Hey, so welcome to our notes for transformations of functions. And on the front of the foldable, we've got some vocabulary that we want to look at together real quick. Right underneath of the title transformations, that's the transformation form equation written in function notation. Okay, the H and the K, we're going to learn that those represent translations. Translation is a transformation that shifts or moves a function's graph to the left or right, up or down. Okay, then the A and the B, if those are negative, that causes a reflection, which is a flip or a mirror image over either the X or the Y axis. Okay, dilation is also affected by the A and the B, but only in absolute value. So we don't worry about whether it's negative because that represents a reflection. So the absolute value of A and B indicate dilations if it's not equal to 1. And a dilation is a stretch or a shrink of the graph. It impacts the slope of the graph from its center point or end point or vertex through the distance to the X or the Y axis. So we have vertical stretches and shrinks, or horizontal stretches and shrinks, depending on the axis that we're headed towards. Okay, rigid transformations are translations and reflections. They're rigid because they maintain the same shape and size as the parent graph. They just move it to a different position on the coordinate plane. A dilation is a non-rigid transformation. Dilations, they have the same shape. You can tell it's a parabola, for example, when it's been dilated, but it's a different size because it's been either stretched or shrunk. Another word for shrink is compression. So if you think about like a slinky, you can stretch it out real far or compress it or shrink it down. It's still recognizable as a slinky, it's just been modified in it with respect to its size. Okay, so that's our vocabulary for transformations. If you look at the parent graph foldable that we made in the last lesson and flip that over to the back, you'll see the transformation rules listed out here. If you weren't able to print that, you're going to want to make sure that you copy those transformation rules from that PDF file into your notes, because you want to have that as a handy reference as we're working through these examples that follow. Okay, so the transformation form is this equation. I just pulled it over to the side here to help us analyze it a little better. And we're going to start by looking at the K in that equation. So in transformation form, it's always a plus K. Okay? And if your K is positive, then that's a vertical translation up. Right? So translation up. And you would find the impact on the point moving up by adding K to the Y coordinate. Now, if you have a negative K, right, that would be f of x minus K, and that is a vertical translation down, right? Instead, if it's a minus, it's going to head down. Okay, then the next letter that we come to is this H, and that's an x minus h in our transformation form. So when you have x minus a positive h here, then that is a translation to the right. Okay, so f of x minus h, that's your translation to the right. If your h is negative, so for example, if you had written it this way, x minus negative h, right? So in our standard form here, x minus a negative h, when your h is negative, that minus and a minus makes that into a plus, x plus h. And that's what's being referred to over here in the transformation rules, x plus h. That's moving to the left. And it seems counterintuitive, right, that x plus h would move to the left, but x minus h would move to the right. But if you think about it this way, that the standard form is x minus a positive h, right, that's the going to the right, if you're x minus a negative h, that negative is the one that's taking it to the left. It's just that when you simplify that negative and a negative, you get the positive in between. Right? So x plus h goes to the left, x minus h goes to the right. And if you're working on ordered pairs, that impact is subtracting h or adding h to the x coordinate of the ordered pair. We'll move it to the left or the right accordingly. Okay, then our next transformation that we want to look at has to do with reflections. So if you have a negative a, right, so if your a in the front of your function is a negative, doesn't matter what value it has as long as it's a negative, that causes a reflection in the x-axis. Okay, if your b is negative, right? So b is your coefficient in front of the x. So if that value is negative, then that gives you a reflection in the y-axis. Okay? And again, it doesn't matter the magnitude of a and b, just whether they are negative is what causes that reflection. Okay? Now, the a and the b don't just impact whether there's been a reflection, they also impact whether there's been a dilation. So A is what we want to look at for vertical stretches and shrinks. So if you have A times the function, if the absolute value of A is greater than 1, so a positive 1/2 would not be greater than 1, but a positive 2 would be greater than 1, right? If a was negative 2, because we're putting that in absolute value, it becomes a positive, right? And it would be greater than 1. So whenever you have an absolute value of a greater than 1, that's going to be a vertical stretch away from the x-axis, okay? And if your a is an absolute value less than 1, so remember this is absolute value, so it doesn't matter if it's negative, only the absolute value of it. So if your a was positive 2 or negative 2, that would not meet this criteria, right, because it wouldn't be less than 1. So what is a number less than 1 in absolute value? That would be a fraction like 1/2 or 2/3. So decimal value, right, 0.3, 0.4, anything between 0 and 1 is going to meet this criteria where we end up with a vertical shrink toward the x-axis. Okay. The b behaves in a similar fashion where we're not concerned about whether it's negative, we only care about its magnitude and absolute value. So if the b, which is the coefficient on the x, if that b in absolute value is greater than 1, then that's going to cause a horizontal shrink toward the y-axis. Okay, if the absolute value of the b is a fraction or decimal between 0 and 1, right, because the absolute value has to be less than 1, then that causes a horizontal stretch away from the y-axis. Okay, so the b impacts the dilation with respect to the y-axis. The a impacts the dilation with respect to the x-axis. Okay, so that's a lot of rules. However, you just keep this reference nearby as we go through them, and the more you practice them, the quicker and easier they become, and it just starts to go pretty quickly if you get a lot of examples under your belt. So let's start with example 1. We have f of x equals 7 plus 1/2 times the quantity x plus 1 squared, and then minus 10. So you want to be careful before you start grabbing values and saying whether they're a, b, h, or k. Students are tempted in this example to just say k is negative 10 because it's at the end where the k is. But we can simplify this to get it into standard form by combining like terms. So if we take this 7, because the 7 is being added to this product here in the middle, and then combine that like term with the negative 10 to simplify, then our standard form is going to look like f of x equals, because we're trying to, in standard form, we're trying to get it to match this transformation form. So we'll have f of x is equal to 1/2 times the quantity x plus 1 squared, and then positive 7 minus 10 would be simplified to negative 3. So now I can see that it's, once it's in standard form, that my a, right, a is the number in front of the function. My a is 1/2. Okay, a being 1/2, that tells me the dilation with respect to the x-axis. So under non-rigid transformation, because it's the absolute value of a is less than 1, that is a vertical shrink of 1/2. Okay, and that's going to impact the slope from the vertex to 1 unit to the left or right of that value. Okay, the next one I come to is my b. Okay, and b is the coefficient on x. Since we don't see a number in front of x, that tells us that the b is positive 1. Okay, so there is no reflection or dilation in the horizontal. Okay, then the next value that we come to is the h. And since this is x plus 1, but our form here for transformations is x minus h, we just need to recall that that's the same as x minus a negative 1, right? Because a negative and a negative is a positive. So my h is equal to negative 1. Okay? And that h being a negative 1 tells me that I have a rigid transformation which moves this graph to the left 1 unit. Okay, then comes my k, and k is equal to, and this is plus k. When I look at my standard form over here, that's the same as plus negative 3, right? A positive and a negative is a negative. So minus 3 is plus a negative 3, so the k is equal to negative 3. Okay, so now I know my a, my b, my h, and my k. Since the k is negative, I have a rigid transformation that's making my graph go down 3 units. Now before I can sketch that graph, I need to know what type of function I'm looking at, and because there's a square here, that tells me that this is a quadratic. Whoops, that looks like an S. Let's fix that. So quadratic QUADRATIC. And if you don't recall what the parent graph of a quadratic function looks like, it is a parabola, which is a U-shaped graph. And that parabola goes through the anchor points 0, 0, 1, 1. So this is 0, 0, 1, 1, and negative 1, positive 1. Those are the anchor points from our parent graph's notes. So if I'm going to take that parent graph, which is at a vertex at 0, 0, but I need to move that graph to the left 1 and down 3, that means I'm going to go down 1, 2, 3 to negative 3 to the left 1, and now the vertex, instead of being at 0, 0, is at negative 1, negative 3. Okay, that's my new vertex. Okay, then the parent graph, it went from 0, 0, up 1 over 1, right, to get to 1, 1, or up 1 to the left 1 to get to 1, negative 1, positive 1. That would be a slope of 1 over 1 for the parent graph. Because I have a vertical shrink of 1/2, we're going to use that a over 1, right, as the slope to get from 1 unit to the right or left of the vertex. It only works 1 unit right or left of the vertex. You cannot go any further. And notice it's the a over 1. It's not rise over run like this, right? A is your rise, and our a is 1/2. So I go up 1/2, and then to the right 1. That's a over 1. Back to my vertex, I can go up 1/2 and to the left 1. And that would give me the 3 transformed anchor points of my quadratic function. Now, it's difficult to tell from just 3 points what is happening up at the top here in the graph, and we want to make as accurate a sketch as we can. So using the graphing calculator here, I'm going to just pick a value for x and find a y that goes with it to get me another point on this graph. So if I put in my equation 1/2 parentheses, but instead of x, I'm going to put in, let's do -3. So -3 for my x plus 1, close the parentheses, then I have a square, and then that's -3. Right? That's my standard form that I wrote out here. I press enter, and that tells me now that -3, -1 is on this graph. So I'm going to plot that point here at -3, -1. Because parabolas have symmetry, I can reflect that point over the axis of symmetry through the vertex, and that means 1, -1 would also be a point on this graph. Okay, and if I hit second enter on the calculator, that retypes what I had. And now I'm going to just put in -4 for my x, so I can see what's happening on this side of the graph. Press enter. So when x is -4, I have a y at 1.5. So I can plot that point, then reflect it over the axis of symmetry, and 2, 1.5 would be another anchor point, or guide point. So now I've got enough points here that I can kind of sketch that U-shaped parabola through those anchor points and guide points, and that would be my sketch of the graph of this given function for the parabola using its transformations. Okay, so go ahead and at this point you can pause the video, and then when you're ready, come back after you've tried the part B of example 1, and then we'll go over the answer to that together. Okay, so welcome back, and we're going to start by putting this rational function into standard form to match this transformation notation over here on the side. So remember that the parent graph of a rational function is f of x equals 1 over x. So that tells me that this 2 is actually my a, right? So here my a is equal to 2. So in standard form, I would start out with f of x is equal to 2, and then times the quantity, 1 over x minus 3, because that x minus h, right, tells me now that my h is 3. Okay, and then on the outside of that is my plus k, and here on the outside of my equation I have a plus 1, and so that tells me that the k is equal to 1. And the b is the coefficient on the x, and when we look at this standard form, there is no number written in front of x, so that tells me that b is equal to 1. Okay. So my type of function, this was a rational function because the variable was in the denominator, and a rational function graphs a hyperbola. Remember, that's the graph that has asymptotes, so I would have a curve here and a curve here, right? And then the asymptotes shaped those curves along the x and y axis. Okay, so that's the parent graph that I'll be looking at. And I'm going to make this a little bigger so we have some more room. Okay, so now let's describe our transformations. So if k is equal to 1, that's a rigid transformation that's going to move the graph up 1 unit. And then h is positive 3, so that moves us to the right 3 units. Okay, and the parent graph, remember, its asymptotes intersect at 0, 0, and then its anchor point, it goes through 1, 1, and negative 1, negative 1. So that rigid transformation is going to do those up 1 and to the right 3 on those guide points. So the intersection of my asymptotes, instead of being at 0, 0, I go up 1 unit and to the right 1, 2, 3. And that would be the intersection of the asymptotes. So I'm going to go ahead and dash in those asymptotes, vertical and horizontal, because those are what will guide the graph. And then next I have my reflections to look at. Since A and B are both positive, there are no reflections. And I move on to non-rigid transformations, which would be dilations. And when I look at this graph, I have a dilation here because A is 2. That's going to be a vertical stretch of 2. Okay, and remember that that tells me the slope 1 unit away from the center or intersection of my asymptotes. Boy, I made a mess of that word. Let's try that again. Slope, S-L-O-P-E. There we go. So the slope 1 unit away from the left and right of the center point, in this case, the intersection of the asymptotes, right, is going to be 2 over 1. So I start here at my intersection. I go up 1, 2, and to the right 1. Or down 1, 2, and to the left 1, because I have to follow that same shape of the hyperbola of the parent graph. Okay, and then if I want to get a couple more anchor points, I can use my calculator like we did in the last example. So I'm going to put in, let's see what we have behind here. Let's put in 5 for the x. So we'll have 2 times the quantity, 1 divided by. Since I've got a binomial in my denominator, I'm going to group that in parentheses and put in 5 for my x. So x minus h, then close the parentheses on the function, and then plus 1, enter. And my answer is 2. So when x is 5, y is 2. So I'm going to go ahead and sketch the point 5, 2. And then I know that this is coming along those asymptotes, bending through bending through those guide points and approaching the other asymptote. Since hyperbolas have symmetry, I can use that same pattern then to get a guide point on this side, and then I'm sketching along those asymptotes, right? And that would be my hyperbola. Okay, so we were able to use transformations now to sketch the graph of that rational function up there at the top. Okay, so go ahead and try this one on your own. You're going to take this and put it first in standard form so that you can recognize where your transformations are. Tell me what type of function it is, what transformations it has, and then go ahead and make a sketch of the graph, and pause the video and then come back when you're ready to check your answer. Okay, so welcome back. And when we put this into standard form, okay, we're going to end up with a negative out front because that's our a, right? Then the square root of the quantity x plus 1. this 2 out front and this 7, those are like terms that we can combine. 7 plus 2 is 9. So standard form is going to look like this. And the a then in standard form is -1. And if a is -1, that's a reflection, and it's a reflection in the x-axis. Right? If it was the b, the number in front of the x, the coefficient in front of the x that was negative, then it would be a reflection in the y-axis. It is possible to have both. It's possible to have a reflection in both the x and the y-axis if these were both negative, a and b. But we only have one negative on the a, so that's a reflection in the x-axis. The b, the coefficient in front of the x, is a positive one, which means there's no dilation, right? No dilation in the vertical or the horizontal because the absolute value of a and b are both 1. And then we've got our h, and since this is x plus 1, our h is a -1, which is a horizontal translation to the left 1 unit. And then the k, the constant here at the end, it's a +9, so k is +9, and that is a vertical translation up 9 units. Okay, so we have no translations down or to the right, no dilations, right, just a translation up 9, left 1, and a reflection in the x-axis. Okay, since this is a radical here with an index of 2, the type is a square root. And if you recall, the parent graph of the square root function passes through 0, 0 with its endpoint 1, 1, and then goes off to make the top half of a sideways parabola. So to sketch that graph using the transformations, right, instead of our endpoint being located at 0, 0, we have to go up 9 and to the left 1. So to the left 1 puts me at -1, then up 9 units means my endpoint is up here at the point -1, 9. Okay, now there's been a reflection in the x-axis, so instead of going up 1 and to the right 1, I'm going to go down 1 and to the right 1, and that puts me at this point 0, 8 as my guide point. Okay, and then I want to get at least one more point that I can use to guide my graph here. So I'm going to put in a value for x, and you can do this with mental math if you think about what your perfect squares are. So if I were to put in like 1, for example, for x, I would have to know the square root of 2, which isn't a perfect square. But if I put in 3 for x, right, 3 plus 1 is 4, square root of 4 is 2, so that would be -2 plus 9 is 7. So that, just doing the mental math there, would be the point 3, 7. So I could go over here, 1, 2, 3, and then down just a smidge, and that would put me at the point 3, 7. Wow, that does not look like a 7. Let's try that again. So that would be 3, 7. That looks better. And then I go from my endpoint through those guide points, and that would be a sketch of this square root function. Okay, if you're not good with perfect squares and you want to use your calculator instead, right, we could put in a 1 for the x, so that would be negative square root of 1 plus 1, then close the parentheses on the square root, add 9, right, and that would be the point 1, 7.6 if we rounded to 1 decimal place. So again, you want to pick as many guide points as you can to get an accurate sketch, but feel free to use some mental math there to make that a little quicker for yourself. Okay, so hope that helps. I know this was a long video, but it takes a lot of thinking and effort to reference all of those transformations. But like I said, the more you do them, the faster they go. So go ahead and give some of these a try.